Okay, so this is our next physics talk. This is a mammo physics talk. So, why is mammo different than regular X-ray? Why isn't it the same as just taking a chest X-ray or an X-ray of an arm or a leg or whatever? The difference is that breast cancers and breast tissue are very similar in density. Their attenuation is very, very close. So you have to use very low energy to take advantage of that. So I'll illustrate this here. So this is the bottom axis of this graph is energy increasing in this direction. So glandular tissue and fat are pretty close together, but a cancer and glandular tissue are even closer together. And you can see that down here at normal energy, which is the typical energy that's used for diagnostic X-ray, which is around 50 keV, they are basically right on top of each other. So you have to use a lower energy here, around 20 or so, to be able to see where they're separating out. Another reason that mammo is different is that it requires increased spatial resolution because you're trying to look at little tiny things like calcifications. So here's a typical situation. You may remember this from one of our earlier lectures where you've got a typical cathode anode setup and fires down through there and generate an X-ray. And that's made out of tungsten, and your kVp is around 50 to 120. Well, mammo is different. Instead of using tungsten, we are going to use either moly or rhodium. And instead of having 50 to 120 or so with our kVp, we're going to have 25 to 30 because we want to use that lower energy, and we're trying to be able to exaggerate that difference between glandular tissue and a cancer. So here's a typical spectrum for moly, and this combination of low kVp and a low Z moly is going to give high characteristic X-rays with a low background breaking radiation. Now, just as a quick refresher, remember that there's this entity referred to as the K-edge, and this is when you have a spike in the chance that a photoelectric effect is going to happen. Right where the photon energy and electron binding energy are essentially the same. This is a sweet spot. It gives you maximum contrast. So what we will do, or what is done with mammography, is that a filter is placed with a specific K-edge. And the purpose of this is to block both high and low photons. You want to try to basically make the beam monoenergetic, or as close to that as you can get. Now, the benefit of removing the low energy photons are that they are contributing only to dose, and they're not helping with image contrast. Okay, so here we go. We've got, here's our regular moly spectrum, and we'll place our filter across it with that spike of a K-edge here. So blocking so the very low energy ones are going to get attenuated, and they're going to get blocked easily. And then we've got our K-edge here, which is going to spike, and what we're going to end up with is a spectrum that changes and looks something like that. So that gives us sort of our maximum. That's the ideal energy, is almost this monoenergetic energy for maximizing our image contrast. So we've got a beam that's basically monoenergetic between 16 and 23, and energies less than 15 or greater than 20 or so are basically filtered out. So there's a couple of different filter combinations and anode combinations that you can use. You can have a moly-moly, and the moly, so moly target with a moly filter. You can use a moly target with a rho filter, or you can use a row target with a row filter. And they're increasingly stronger in their energy as we go across here. So row is what you would use to row yourself across the dense breasts. So row your boat across these denser breasts. That's the way that I remember that. Now you can also use moly. You can also have a moly anode that's combined with an aluminum filter, and that will also produce a harder beam. That's sort of a newer thing. Think about the row I think it's more testable. So why not row moly with a row target and a moly filter? Because what you're going to end up with is if you place the so this is a normal situation where you've got a moly. Notice that the filter lands in front of these characteristic X-rays. That's where your K-edge is there. This is what would happen if you did a row moly situation where the K-edge is actually less than the characteristic X-ray. You could imagine that would so you're knocking out the stuff that you want to use. Instead of getting rid of the garbage, you are getting rid of a lot of the good stuff here as well. So you would never do a row anode with a moly filter. And believe me, that will be a distractor for sure. So that is a combination that does not exist in diagnostic imaging. Okay. So I mentioned this before, that mammography requires a really, really good spatial resolution, more so than you get with normal imaging. So to achieve that, you have to use a smaller focal spot. So to put things in perspective, mammography typically uses a focal spot that's around 0.3 to 0.1 millimeters, relative to general X-ray, which uses a focal spot that's 0.6 to 1.2 millimeters. So we're talking about half the size or a tenth of the size, so it's a lot smaller. Now, what's the downside to this? The downside is that smaller focal spot does not tolerate heat as well. So you have to make some adjustments, and what you do is you have to lower your MA. Otherwise, you would melt the anode. So the MA is limited to about 50 for 0.1 and 100 for 0.3. So the smaller it is, the less heat tolerance it has, and the lower the MA you have to have. Now, since you're lowering your MA, you have to extend your exposure time. So generally, you still try to keep your exposure time to under 2 seconds. Now, this is another thing that I mentioned before, but I'm going to mention it again, this idea of the heel effect. So especially with mammography, it's important to line up the cathode with the same side as the chest wall, so that because you have loss of energy on the anode side, which is the nipple side, and that's, the breast is getting progressively thinner as you get away from the chest wall. So taking advantage of that. And that's pretty much that. So another difference is that in a standard diagnostic tube, you've got a window here. So and that is just made out of Pyrex glass. That's not used in mammography because it causes excessive attenuations, especially at those lower energies. And those lower energies are the ones that you want to use in mammography. So they use a beryllium exit window instead. So there, something like that. I'm going to keep those lower energy X-rays. Boom. All right, so here's another concept in breast imaging, is that the breasts aren't just thrown down on the plate in X-ray, they're compressed, right? And there's a whole bunch of different reasons why they're compressed. The reduced breast thickness means there's going to be less scatter. And if you remember from our prior lecture, a thicker body part will have more scatter, so a thinner body part will have, or a thicker body part will have more scatter, so a thinner body part will have less scatter. Also, this allows for a lower KVP to be chosen. If you remember, the photoelectric effect dominates more at lower KVPs, and higher you get more Compton scatter as well. So that lower KVP equals less scatter, which equals improved contrast, all that made possible by a compressed breast. Also, with reduced thickness, you can have less MA, so you get less dose. From that perspective, the breast doesn't move. Remember, you have to have this prolonged, because your MA is more, you have to have a little bit longer exposure. So that creates potential for motion artifact, but if you smash the breast down, they can't move anymore. A smashed breast is actually closer to the bucky, which is going to create less geometric magnification. And with less motion and less geometric magnification, you've got improved spatial resolution. And lastly, you're going to get your tissue spread out more, so you're going to have less overlap, and that's going to give you less callbacks. So all these different reasons here. Now, another thing that happens is that you're typically using a grid. Now, since the breast is placed in compression and you're using a lower KVP, both of which intrinsically are reducing your scatter, a smaller grid can be used. The grid, of course, removes scattered photons, which in itself reduces the dose, but you can't use the same technique that you would be used without a grid is the same as a grid. Otherwise, you'd end up with underexposure. So ultimately, you have to turn the technique up, and ultimately that leads to an increased dose as a result of a grid, which is something that we talked about before. So the grid actually it initially reduces the dose, but that would create an image that was non-diagnostic, so you have to eventually end up increasing the dose. So bottom line, for the purpose of multiple choice, is that a grid increases the dose. Now, for magnification, it's done with a smaller focal spot, and it's done with a smaller paddle, and it's done with no grid. Instead, an air gap technique is used. So if you remember back to this, if we increase the distance between the object and the detector, then that will increase the magnification. So an increase in air gap will increase the magnification. And if you increase the air gap, you're also going to increase the dose, because the automatic exposure rate controlling the imaging quality is going to ramp up to compensate for less photons hitting the detector. So it's the same thing basically as the grid. All right, so let's just do a quick review of regular mammogram versus a magnification view. So in a regular mammogram, the breast is in direct contact with the bucky. With a magnification view, we've got an air gap. Remember, we're going to use a grid in a normal mammogram, but we're not going to use a grid with magnification view. Instead, we're going to use an air gap technique. A large focal spot, large relative, remember, it's still smaller than it would be for a diagnostic X-ray by, between half and a tenth of as much. But when you do a mag view, you're getting even smaller. And the paddle size is also smaller. And because you've got an even smaller focal spot, you've got to go down lower on your MA, so you've got to go up on your exposure time to avoid melting the paddle or the target, the focal spot. All right, so now this is just as a summary, and this is super high yield, right? Because anytime you've got a difference between two things, it makes it very high yield. This is a mammogram versus a general X-ray. So low energy versus high energy. Remember, the reason we do that is to accentuate those differences. The anode is moly or Rho relative to tungsten. You've got low MA because you've got a smaller focal spot, high MA because you've got a regular focal spot, longer exposure time so that you're not underexposing because you had to go down on your MA. You can get away with a fast exposure time with general X-ray, and the advantage to the general X-ray is that you're going to have less potential for motion artifact mammograms have more potential for motion artifact, but they compensate for that by pinching the breast in a compression device. Small focal spot for improved spatial resolution. And then there's that beryllium window because you can't use the regular glass because that takes out those low energy X-rays, which are the ones that we want to use for optimizing our contrast. And then there's a difference in dose, which is this idea of air kerma, which, something we can talk about later. But just, there is more dose mammo because there's longer exposure times, because there's a grid, and all those kinds of things. Okay, that's the end of this talk.